Welcome back to my lectures on Galois theory. Today we are going to start a new topic. It's on finite fields. In this topic, we are going to discuss on how to characterize a finite field, meaning a finite means there can be only a finite number of elements. So can we create a field with any number of elements? And once it created, what are the elements? Can it define the elements? In group theory, you know that you can create a finite group of any size, like Zn is 1, 2, and minus 1 for any integer n. So you can create a group with any number of elements. We can create a finite group with any number of elements. So is it possible to create such structure in field? Can you create a field with any number of elements? Or in particular, can we create a field with say 6 elements? And once you define what are the elements, can you define the elements? Okay, so that is what we are going to do in finite fields. So before we go there, I want to touch base with some basic definitions and some results which you already established earlier. The one is, let us take a field. You know ZP is a field because when P is prime, 0, 1, 2, 3, P minus 1. Then let us not take P. Let us take a concrete example. Okay, Z3 or Z5. Let's take C5. C5 is a field. So 3, 4. Now you take the elements from C5, not including 0. 1, 2, 3, 4. Okay, you already have multiplication defined here. So this 5 with multiplication is an abelian group. Okay, that means, so if in general, if you take ZP star with the multiplication is an abelian group. See, abelian group, this multiplication is multiplication modulo P. So if you multiply 4 into 2, it's actually 4 times 2 is equal to 3. So that is how you multiply here. And the identity is always going to be the multiplicative identity of the field. One result we already established in the extension field is this. Let E be a finite extension of degree n over a field of a finite field f of q elements, then E contains q to the power of n elements. You already did this. And there is another result that we established in prime and maximal ideals. That is, any field, not necessarily finite, is either of characteristic P, P being prime, and includes a subfield isomorphic to ZP, or a characteristic 0 and includes a subfield isomorphic to Q. This is a very powerful result. You already established this one in prime and maximal ideals. Meaning, if you take any field, then either this has to be a characteristic P for a prime P, or it has to be a characteristic 0. If it is P, then it includes a subfield isomorphic to ZP. If it is 0, then it includes a subfield isomorphic to Q. Basically, when it is characteristics P, then it is finite. Otherwise, it is 0. These two results we are going to use to find out how many elements are there in a finite field. So, just to explain the Castex game, a field F is of characteristic P if P times A is equal to 0 for all A in F, and if there is no such P exists then the characteristic of f is 0. So for any finite field, the characteristic is greater than and that means the characteristics of f is p for some p, because any field, either the characteristics has to be 0 or p, but if it is finite, it is greater than 0. That means it is of characteristics p for a prime p. We are going to combine these three results. We are going to combine these three results together to find out the number of elements in a finite field. So this says that if a finite field is of characteristics p, and if it is characteristics p, then it includes a subfield, and includes a subfield isomorphic to Zp. So a finite field E includes a subfield isomorphic to Zp. We are excluding this because its characteristic is not 0. So we are reducing this result to here. This implies E is a finite extension over Zp, because this includes a subfield of Zp, means E is an extension of Zp, and because E is finite, it has to be a finite extension. So let the degree of E over Zp be N. Okay, and we know that Zp contains p elements. Now we use this result. E is a finite extension of degree n over a field f with q elements, with p elements. Then E contains p to the power of n elements. So if it is a finite field, it has to contain p to the power of n elements for some p and for some integer, positive integer n. Now we'll answer our first question. Can we have a field with 6 elements? The answer is no, because you cannot express 6 as a power of a prime number. 6 is 2 into 3. There are 2 co-prime numbers there. Now we know the number of elements in a finite field. Our next objective is to define the elements. The way we are going to define is to set a property of the element. So, let E be a finite set, finite field, sorry. Let E be a finite field of p to the power of n elements. Because any finite field has to have a p to the power of element for some prime p and integer n greater than 0. So let us consider the group, multiplicative group of non-zero elements of E. So let E star be the non-zero elements, be the group of non-zero elements of E. So that implies E star contains p to the power of n minus 1 elements. So let alpha belongs to E prime. It doesn't have 0. Otherwise it is same as E. All elements from C other than 0. So this means alpha to the power of p to the power of n minus 1 is 1. Because if you take a finite field with the product, like let us say Z3, 1, 2 star, then 1 square is equal to 2 square is equal to 1. 2 square is 1 because 2 square is 4, mod 3, 1. So if you take C5, 1, 2, 3, 4, then we have 1 to the power of 4 is equal to 2 to the power of 4 is equal to 3 to the power of 4 is equal to 4 to the power of 4. Or are 1. So that's what I'm saying here. So if a finite field has got p to the power of n minus 1 elements for any element, this is true. And this is equivalent to saying that alpha to the power of p to the power of n is equal to alpha. That means alpha is a 0 of the polynomial x to the power of Pn minus x, because this implies actually alpha to the power of Pn minus alpha is equal to 0. And alpha is any element from here. That means any element of E star is a 0 of x to the power of Pn minus x. And of course, if you add 0, it will become e. And 0 is also a 0 of this polynomial. And 0 is also a 0 of x to the power of Pn minus x. So that implies any element of E is a 0 of x to the power of Pn minus x. And x to the power of Pn minus x has at most p to the power of n elements. What does that mean? Here it says that every element of E is a 0 of this. Here I am saying that this polynomial has at most p to the power of n elements. And we know that E has p to the power of n elements. So that means every element that means E contains precisely the zeros of x to the power of Pn minus x. So the result is E is finite, E is a finite field, then E has p to the power of n elements, and E is equal to alpha, where alpha is a 0 of x to the power of n minus x. So we totally defined that finite field. It has got p to the power of n elements, and we know all the elements of that field. Now let us construct a field, which we already did it, but we want to revisit one more time. Let us create a field, a finite field E with 4 elements. 4 elements is possible because it is 2 square. We already created this field earlier as an extension of Z2. So it is an extension of Z2. The way we defined this field is like this. E contains the zeros of the irreducible polynomial x square plus x plus 1 in Z2x. This is an irreducible polynomial because if you substitute zeros and 1, it doesn't be 0. It's not going to be 0. And we know that the elements of E are 0, 1, alpha, 1 plus alpha. And we already created a multiplication and addition tables on this earlier. So I'm not going to go all this stuff. But I want to compare what we have already. What we have is E contains 2 square elements from our results just established earlier, and E has the elements alpha such that alpha is a 0 of x to the power of 2 square minus x. That is what we established earlier. These two are actually identical. Why? This is actually alpha. Alpha is a 0 of, this you can write it as x4 minus x. And this is actually equal to alpha. Alpha is a 0 of x times x cubed minus 1. And that you can write it as alpha is a 0 of x times, this you can write it as x minus 1 times x square plus x plus 1. So it doesn't say that this has to be irreducible. Actually it is not, because it actually reduced to polynomial of lower degrees here. So what are the zeros of this? The zeros of this is 1 is actually 0. The first one is 0 because if x is a 0 of this, and of course because x minus 1 is a factor of this, 1 is a factor. 1 is a 0. Then you have x square plus x plus 1. That is exactly what we have here. And 0 of x square plus x plus 1 is alpha and 1 plus alpha. Here what we did is, we are trying to find out the elements outside Z2. That is alpha and 1 plus alpha. Here we totally define that finite field. The way we arrived at alpha and 1 plus alpha is like this. If alpha is 1 of the 0 of x square plus x plus 1, then E is equal to 0, 1, alpha, 1 plus alpha. What we did is actually x square plus x plus 1 divided by x minus alpha, and the remainder is going to be, not the remainder, the quotient is going to be x minus 1 plus alpha. So in both ways we are arriving at the same conclusion. Okay? Let us define a new term, nth root of unity. Let f be a finite field and alpha belongs to f. Then if alpha to the power of n is equal to 1, alpha is called the nth root of unity. And if there exists no m such that alpha to the power of m is equal to 1 and 0 less than m less than n, then alpha is called the primitive nth root of unity. Definitely alpha is not equal to 0, because if it is 0, definitely this will not satisfy. So 0 is not an nth root of. We'll do an example here. We'll take the same extension of Z2 that contains 4 elements: 0, 1, alpha, 1 plus alpha. Here 1 is actually nth root of unity. Nth root of, actually 1 is actually 1th root of unity. Root of unity. N is equal to 1. What about alpha? What is the condition here? Alpha square plus alpha plus 1 is equal to 0. Let us take alpha square then. Alpha square is actually alpha plus 1, because if you take minus alpha minus 1 and minus alpha is both alpha plus 1. So this is, so alpha cube is what? Alpha times alpha plus 1. That is alpha square plus alpha. And that is equal to minus 1 because of this equation, and that is 1. So alpha is also a nth root of unity. N is equal to 3. Similarly, you can find out 1 plus alpha square is equal to alpha square plus 2 alpha plus 1. This is alpha square plus 1. Alpha square plus 1 is alpha. So 1 plus alpha cube is equal to alpha times 1 plus alpha is equal to alpha square plus alpha is equal to 1. So 1 plus alpha is also an nth root of. Okay. So these two are primitive alpha, and 1 plus alpha are primitive third root of unity in Z2 bar. Z2 bar actually I'm considering as the finite field of 4 elements.